Good morning. Again, empty room, locked door, so no mask. Chapter 11, Evidence of Evolution. Evolution is by far the most controversial subject we will talk about in a biology class. Most of that stems from misinformation and misunderstanding. I'll try to settle a little bit of that today. I mean, there's no way I'm going to change anybody's mind about if they have deep held beliefs. But again, evolution is a theory. This is the best explanation for the way things are in the world. I'm not satisfied with my camera angle, so forgive me. But this is, again, the theory of evolution. The theory states that an asteroid some 45 meters wide created a mile-wide Barringer crater in Arizona in some 50,000 years ago. We know this happened. We know there's a crater. We can date that it happened approximately that many years ago. Scientists use that information to infer, such as the potassium boundary layer, that an asteroid impact near the Yucatan Peninsula in Mexico some 65 million years ago caused the mass extinction of the dinosaurs. We've seen this in popular culture. We've seen it in movies or kids' cartoons that talk about what happened to the dinosaur. But a mass extinction is a simultaneous loss of many lineages from Earth. There have been, again, archaeologists tell us that there have been several of these mass extinction events that have happened. Where there are movies. Just watched a movie this past weekend with my wife called Deep Impact, which was about an asteroid that was hurtling toward Earth, and it was going to cause an extinction event. Then when more than likely, this 45-meter wide crater, asteroid that hit the Earth some 50,000 years ago, I'm sure caused environmental upheaval, probably changed climates, but it was not really considered a mass extinction event. The one 65 million years ago, this was a much larger, this was, I recall from my basic classes I took at UALR many years ago, this asteroid was like a mile wide. So again, caused in theory, the extinction of the dinosaurs. By the late 1800s, naturalists were seeing patterns in where species live and similarities in body plan. You see certain, and I'm relatively sure here because I've looked through these slides a moment ago, there's going to be pictures of some birds from certain areas of the world. But we began to notice that certain types of animals appeared in certain places and not in other places. There may be, for instance, an animal in the southern part of Africa and South America that were similar, but the animals from the northern part of Africa and the northern part of South America not so similar. Well, that's called biogeography. It's the study of the patterns and geographical distributions of species and communities. Why is it that the marsupials are mostly found in the southern hemisphere, in the southern part of the planet? If you take the planet and divide it into a north half and a south half, why is it that the bulk, almost all of the marsupials, are from the south part and not from the north part? Why are there no marsupials and marsupials, I mean things like kangaroos and possums? Why aren't there any of those in Europe? Why are they found in Australia and New Zealand and South America? Why is that? That's biogeography. Comparative morphology is where we study the anatomical patterns in body plans. Do they have, 5 fingers or hands and feet? What is the morphology means the shape, and we are comparing shapes. So what is it about this animal and this other group of animals? How are they similar in body shape and body plan? Naturalists in the early, again, 1800s and so, had trouble classifying organisms that are very similar in some features but different in others. They have problems with is it a lizard or is it a salamander? They look very similar. They have the same sort of body plan. So where do we find a new one? Where does it go? Is it a lizard or is it a salamander? Naturalists studying body plans were confused by vestigial body parts with no apparent function. Human beings, we have an appendix. What's the appendix for? Do we need it? Well, clearly we don't need it because 40% of Americans at some point in their life have their appendix removed. The gallbladder, is it a needed item? Well, sure it is. Can you live without it? Absolutely. I don't have one. I had mine removed 20 years ago. So that's the vestigial body part is something that we still have, but there's no apparent need for it. If any of you are snake handlers, for instance, the big boa constrictor, the boa snakes, the boa constrictors, the anaconda, the pythons, all of those animals, when they get very, very big, toward the back of their body, they have a little claw that looks like a toenail, and that's a vestigial limb. It is the vestige of what many thousands, if not millions of years ago, was a leg that the animal quit using, and over time it just simply went away, but it's left with that little vestigial part. We can also have similar fossils or fossils of giant animals with no living representatives. Also puzzled the early naturalists when they started digging up, these giant bones in fossil beds that they assembled them as best they could, and it looked like nothing that was on the planet today. One of the most interesting ones, and I just say that you go out and in your spare time do a little reading, are the sloths. There are sloths still living today in South America. They are very slow-moving creatures. They have really, really long arms. They hang from tree limbs. They're tree-dwelling animals. If they get down on the ground, they don't move very well at all. If they have to move from one tree to another across the ground, it takes them a really, really long time. But if you are a fan of the Ice Age movies, Sid from the Ice Age movies is a sloth, and he walks upright and moves very quickly. There was also a giant sloth, which was about the size of a elephant. And again, these animals, the ones we have now, look very little like these ancient creatures. So early naturalists were really puzzled by, they would assemble these things and they would say, well, what is this? There's nothing living today that we know of that compares to it. And the scientific findings did not fit with prevailing beliefs of the 19th century. Basically, the 19th century, the belief was all animals were put on Earth in the form they are now, and they didn't change, and everything that ever existed was still here. That was the idea. The idea of extinction didn't exist. I knew there'd be these birds somewhere. This is an ostrich. Everybody's seen an ostrich. This is a bird called a rhea, which is found in South America. And this is an emu, which is found in Australia. These are all large flightless birds. They are a member of a group of birds called the ratites. Don't worry, I won't ask you to remember that. But they all have a similar body plan. They all have very, very small wings. As a matter of fact, on the rhea and the emu, you can't even see their wings. The ostrich, that is his wing right here, but they are large, flightless. They do not fly, they run. Historically, there were several others of these birds. Right now, the ostrich is the largest of the flightless birds on Earth. There were other birds. There was one called the great moa, which was found in New Zealand. There was one called an elephant bird. These were all much larger. Those two were much larger than the ostrich. But the thing about all of these birds, they're all found in the southern hemisphere. Yes, the ostrich is a little bit of a misnomer because the continent of Africa bypasses. It's found both in the northern hemisphere and the southern hemisphere, but the South America is in the southern hemisphere. Australia, New Zealand, New Guinea, those are all in the southern hemisphere. And historically, the ostrich is in southern Africa as well. Yes, it has migrated to the north, but again, that's a little bit of a confusing point. But all of these animals are native to the southern hemisphere. A couple of different organisms. These are different cactuses. Again, very similar in appearance, found in very different places. As I recall from the notes that don't show up when you run this as a slideshow, one of these is a cactus found in the United States, and the other one is a European cactus or an Asian cactus. I believe that may be incorrect, but basically what we're showing here is these cacti, very similar in appearance, but found on opposite sides of the planet. There was a flurry in the late 17, moving into the 1800s. There were several different naturalists who were looking at things and proposing new theories. There was a Frenchman by the name of Georges Cuvier. He proposed that there were catastrophic geologic forces that unlike those present-day Earth that shaped present-day Earth. Basically, he was a believer in what is called catastrophism. He basically said the reason the Grand Canyon looks the way the Grand Canyon looks is it happened very quickly over a very short period of time. Others believe that things happen very slowly. It's called gradualism. Jean-Baptiste Lamarck was one of the first biologists to propose that changes in an animal over lifetime were inherited. Lamarck proposed a theory called acquired characteristics or inheritance of acquired characteristics. Something clearly, Siri on my phone just recognized me say something and she tried to find out what we were talking about. But Jean-Baptiste Lamarck said that his theory was the theory of the inheritance of acquired characteristics. Basically, what he said was if you acquired something during your lifetime, you would pass that on to your children, like we do with money, for instance. He basically said that animals built up things during their lifetime and then they passed it on to their offspring. The example would be Arnold Schwarzenegger. Most of y'all are maybe have seen some of his movies when he had the really, really big chest and the really, really small waist, and he got that from pumping a lot of weights and lifting weights and exercising. Lamarck's theory basically said that once Arnold Schwarzenegger had developed all those big muscles and that great health, that he would just automatically give that to his children. So his children would grow up to look like him with no work at all. Yeah, doesn't work that way. But this was an accepted theory for a couple of centuries, that we believe that the reason giraffes were as tall as they were is because each individual giraffe would stretch their neck and stretch their neck and stretch their neck to reach the leaves, and as through that giraffe's lifespan, it would get a little bit taller. Well, then it would pass that on, and then the next generation would stretch and stretch and stretch, and they would get a little bit taller and pass that on. So that is the theory of the inheritance of acquired characteristics. Naturalists suspected that the environmental factors also affected the traits over time, causing changes in a line of descent. Environmental factors, the weather got colder, the weather got warmer, the weather got drier, the weather got wetter. As plate tectonics, and we'll talk about that in a minute, move things around, climates would change, environments would change, and the organism would have to change with it. Change in lineage is what we are changing the line of descent. That's evolution. Evolution is a word, again, that causes lots of problems, lots of irritations, lots of upset, lots of hurt feelings. But evolution simply means change over time. That's all it means. The evolution has nothing to do with monkeys turning into humans. It means organisms change. I have talked to people in the past that literally believe evolution says that at some point in history, two monkeys got together and had a human baby. That is not, let me repeat it again, that is not what the theory of evolution is. The theory of evolution simply says that as organisms go from generation to generation to generation to generation, they may change. And you build up enough of those changes, say through several thousand generations, and you're now dealing with an organism at this end that's very different from the organism at the other end. In 1831, Charles Darwin set out on a 5-year journey on a boat called the HMS Beagle. He found, through his travels, unusual fossils and observed animals living in many different environments. We'll talk a little bit more about Darwin, I'm sure. He was influenced by a man named Charles Lyell, who was a geologist, and he wrote a book called The Principles of Geology. He set forth the theory of uniformity. This is the one that used to be known as gradualism, and is still called gradualism in some places. But what Lyell said was that the earth was shaped by gradual processes over long spans of time. That things on earth didn't happen quickly, that major changes in the planet did not happen quickly, they happened gradually over time. Darwin, during his trip, he sent thousands of specimens back to England, including fossils of organisms called glyptodons, and we'll talk about glyptodons in just a minute. Actually, there's a picture in just a second. These fossil glyptodons had many of the same traits as our common armadillos, and if those traits of their common ancestor had changed the line of descent that led to armadillos, what had caused the change? Here's a modern armadillo, which is about 1 foot long. Here is a fossil glyptodon, which is about the size of a Volkswagen Beetle. This is about, it appeared on the planet. They existed up until just about 15,000 years ago. So up until just a moment in geologic time, these animals were crawling around on the planet. These are still running around. You can see these on the side of the road all over Arkansas. These animals actually came up from Mexico. They were originally organisms that lived in Mexico, in South America, and they were not originally found in the United States because the areas where the area between Mexico and the United States, there's a couple of rivers, and these things, while they swim pretty well, didn't swim across the river. They had no need to. And then the other areas where you can cross from Mexico to the United States is desert. And these animals don't reside in desert. They do, but they don't do it very well. And so they're not going to travel great distances across a desert. But along in the late 1800s into the early 1900s, humans did something really, really beneficial for these guys. We started building bridges over those rivers, and these guys started crossing the river. And once they started crossing the river, they then started spreading out through Texas and Arizona, and from Texas all around to the United States, to where now I have to deal with armadillo holes in my front yard every year when they get out there in the spring and start digging up the grubs that are in my lawn. And I have big holes, or well, actually not big holes, they're little holes about the size of a quarter or half a dollar, where the armadillo is digging and sticking his nose down in the hole to pull out the grubs. But glyptodons, armadillos. Thomas Malthus was another early researcher. He stated that a population tends to grow until it begins to exhaust the limited environmental resources. And when resources become scarce, individuals must compete for themselves. Thomas Malthus was the researcher you often hear quoted when people start talking about the planet and the fact that our planet may be getting close to becoming overpopulated. Malthus is oftentimes the man that they refer to, stating that, you know, the planet will only hold so many people. And once we get more than that, then we simply can't produce enough food to feed the growing number of people. And you do see, again, most of his theories are now sort of debunked. If I'm not mistaken, he said that the Earth could only manage to support something like, you know, 300 million people or something. Well, there's 300 million people in the United States. You know, there's 2 billion people living in China. But is there a point where we could overpopulate the planet and get to the point where we can't make enough food to feed everybody? Absolutely. But we're clearly not there yet. Yes, there are pockets of famine and pockets of places in the world where they have overpopulated, but for the entire planet, we have not reached that yet. Darwin realized that all populations must have the capacity to produce more individuals than their environment can support. He basically said that you have to be able to produce more than the environment would support to ensure that your species will always be viable. Darwin also concluded that the process of natural selection through variations in fitness and adaptation is the driving force of evolution. Now, when we talk about evolutionary fitness, generally when we talk about fitness, we're talking about, do you weigh the right amount? Do you get enough exercise? Is your heart rate right? Is your blood pressure right? Yeah, that's fitness. But evolutionary fitness is the degree of adaptation to your environment as measured by your relative genetic contribution to the future generations. In other words, how good are you at getting your genes into the next generation? If you are like, again, no disrespect to anybody, but if you're like Jim Bob Duggar and his wife, who have 19 children, those two people have been very good. They have good evolutionary fitness. They've got a lot of their genes into the next generation. Someone who grows up and never has children, then they do not have good evolutionary fitness. If you never have a child, then your genes, your particular genes, stop with you. Adaptation or an adaptive trait is a heritable trait. In other words, it's one that I could pass on to offspring that enhances an individual's fitness. I pass on my good looks. My good looks give me an advantage over somebody who does not have good looks. And again, this is very simplistic way of looking at things. But if you go to the clubs on the weekend, you know that the good-looking guys and the good-looking gals are much more likely to hook up than an unattractive guy and a good-looking gal. I mean, that's just, I'm sorry, that's just the way things are. And if those good look genes are something that they pass on to their offspring, then their offspring are going to have more luck. In the animal world, deer, which male deers are the ones that get to reproduce the most? The ones with the biggest antlers. So having big antlers is an advantage. And that is a heritable trait. Natural selection, there is differential survival and reproduction of individuals of a population that vary in the details of their shared heritable traits. Natural selection. Nature is going to select. Nature selects for, in deer, the big antlers and the buck that can fight the best. You know, the two bucks come upon a doe at the same time. The two bucks are going to butt heads and push one another around. One of them will finally give up and go away. The other one gets to breed or gets to mate. So that is natural selection. A gentleman by the name of Alfred, his middle name is Russell, but Alfred Wallace proposed the theory of natural selection in 1858, the same time as Darwin. Interestingly, Darwin had written up his work on natural selection and had proposed trying to get it published and taking it to the Royal Society in London. But some friends of his told him that he probably shouldn't because the world wasn't ready for it. It was basically anti-religion, anti the thoughts of the day. And his friends told him, you will probably get in trouble for this. The church may come after you, so probably best not to do this. Some 10 or 15 years later, Wallace wrote his proposal for the natural selection. And he actually sent it to several, just like Darwin wrote his and gave it to several people to read and said, what do you think? Wallace did the same thing, sent it to several people and said, what do you think? One of the people Wallace sent it to, Charles Darwin. Charles Darwin read it and said, hey, this reminds me of my work. And he goes over to the shelf and pulls his off and, blows the dust off of it because it had been sitting there for 10 years. And the following year, Darwin actually then published his On the Origin of Species, which he described descent with modification or evolution. Ultimately, these two gentlemen presented at the Royal Academy in London, the most prestigious naturalist group at the time. And since Darwin had what is called provenance, he was able to prove that he had written his work years before Wallace did his. Darwin basically gets all the credit for the theory of evolution, and the only time you hear about Alfred Russel Wallace is in a class like this, where you're just being told the history. Fossil evidence, most fossils are mineralized bones, teeth, shells, seeds, spores, and other hard body parts. Muscle tissue and skin usually does not fossilize. There are things called trace fossils, which are footprints and other impressions. We can find nests and burrows and trails, eggshells, fecal matter. You can actually buy fossilized dinosaur feces. They make jewelry out of it. It has a name, I forget what it is, but if you just type in fossilized dinosaur poo, you'll find it. And again, you can buy jewelry, little pendants and things made out of it on the Amazon and other places like that. Fossils are relatively rare, so the fossil record will always be incomplete. There will always be gaps in the fossil record because very specific events have to happen for a fossil to form. An animal has to die, and it has to fall in the mud, and it has to be covered with silt and soils, and then certain chemicals have to be present that can leach into the bones and remove the organic matter. So very specific things have to happen for fossils to form. And one of the reasons there are so few human fossils is because of where humans tend to live. We tend not to live in swamps. So when we die, we tend not to fall in areas where fossils are readily going to be formed. Most ancient species had no hard parts to fossilize. Many fossils of bony fishes and mollusks, but there are few fossils of jellyfish and soft worms. Why? Well, bony fishes and mollusks have shells, bony fishes have bones. Jellyfish don't have either of those, and the soft worms don't show much. Fossils of a line with greater numbers than existed for longer amounts of time are more likely to be found as fossils. If there are billions of something and they are around for millions of years, then they're probably going to make fossils. If there are only ever a few 100,000 of some creature and it's only around for a few centuries, then we're probably not going to find many fossils. Ergo, why we don't have many human or human-like any hominid fossils, because they weren't around very long, and up until just the last few hundred years, the populations of human beings on the planet was not very big. Up until modernization and industrialization, the population of humans on this planet was reasonably small. The age of rocks and fossils can be determined using radiometric dating. This is not to be confused with carbon dating. Carbon dating has to be done using living or once living organisms. Rocks can't be carbon dated, but they can be radiometric dated. They do that by measuring certain radioactive isotopes and how much of them there are. A half-life is the time it takes for half of a quantity of a radioisotope to decay into its daughter elements. We're not going to go into the chemistry about radioactive and decay and breaking up into daughter elements. We're not going to worry about that. We're just going to know that radiometric dating measures the level of radioisotopes, and it estimates the age of a rock or fossil by measuring the ratio of the radioisotope with its daughter elements. If the ratio is, I don't know, 5 to 1, then 5 half-lives have gone. And what is the half-life? Well, then we multiply whatever the half-life is by 5. Not going to ask you to do that. Simply know what we use radiometric dating for. Carbon-14 dating of a fossil. Again, this has to be something that was once living. Long ago, carbon-14, carbon-12 were incorporated into the tissues of this nautilus, which is a shell still swimming around in the ocean. Both of these isotopes were part of organic molecules in the animal's food. C12 is stable, C14 decays. But the proportion of these two isotopes in the nautilus tissue remain the same. Why? Because the nautilus continues to gain both types during life. The nautilus then dies, it stops eating, therefore the ratio of C12 to C14 will now start to change because no longer bringing in new carbon, the carbon-14 supply is not being replenished. Now it will start to decay. The carbon-14 is represented by the red dots. Carbon-14 decays into nitrogen. Again, I will not ask you what element carbon-14 decays into. Simply that it does decay. After 5,730 years, half of the carbon-14 has decayed. Now here's the thing people get into a lot of trouble with is, well, if it has a half-life, then you can only measure 2. Because after 2, you've used up all of it. No, it's always only half. So after 5,700 years, half of this will be gone. Half of those red dots will be gone. After another 5,730 years, half of what was left will be gone. And after another 5,730 years, what was half of then was left was be gone. Best way to show this in a simple form is an old story, a joke. A frog is 10 feet from a pond. He's going to jump to the pond. Each time he jumps, he covers half the distance to the pond. How many times will the frog have to jump to get to the pond? And almost everybody will instantly say 2. You didn't read the question. Each time he jumps, he covers half the distance to the pond. So the first time he jumps from 10 feet to 5 feet. The next time he jumps, how far does he jump? He's only covering half the distance, so now he's jumping 2.5 feet. The next time he jumps, 1.25 feet. The next time he jumps, whatever half of 1.25 is. Theoretically, will he ever get to the pond? No, because he's always only covering half the distance. That's what we're doing here. Every 5,730 years, half of the red dots are going to disappear. So we've got 50 red dots, then we're going to have 25 red dots, then we're going to have 12 red dots, then we're going to have 6, then we're going to have 3, etc., etc. So that's the way you do. So you figure out how many half-lives have been done. So fossil hunters discover the fossil, measure its content of C14 and C12. They use that ratio of isotopes to calculate how many half-lives have passed. For example, if 1/8 of the ratio is living organisms, if it's 1/8 the ratio of living organisms, so we take a sample of a living nautilus, how much C14 to C12 is there? How much is there in this? So we say it's 1/8. So we've got half of a half is a quarter, half of a quarter is an eighth, so 3 half-lives have spent. So must have passed since it died, 3 half-lives. So 3 times 5,730 is 17,190 years. So the fossil is approximately 17,000 years old. The missing link. This is the one everybody who talks about human evolution wants to find. We all want to find that missing link. What is the link between more primitive humans and modern humans, more primitive human-like organisms and modern humans? So, example, discovery of intermediate forms of cetaceans. What are cetaceans? Cetaceans are whales. The whales are cetaceans. DNA sequence comparisons indicate that artiodactylids, hooved land mammals, things like horses, were ancestors of modern cetaceans. In other words, we look at the DNA of hooved land animals, and we compare it to the modern whales. You know, the right whale, the humpback whale, the blue whale, all of those whales, the sperm whale, and we compare them, and we see that there are a lot of relationships, a lot of likeness between the DNA of cetaceans and the DNA of modern hooved mammals. We have found some fossils. Don't worry about these scientific names, but these are organisms that had whale-like skull bones and ankle bones in the same skeleton. In other words, their skull looks like a whale, but with ankle bones, that means they still have legs. Modern cetaceans have no remnant of an ankle bone, so when we look at skeletons of, again, the humpback whale, the right whale, the blue whale, they do not have those ankle bones present. Again, cetacean skeletons. Here is a small terrestrial animal, lived about 30 million years ago. Again, don't worry about scientific name, but let's look at these bones right here. That's the bones of what would be considered a hind leg. Here is one of those creatures listed that said it still had the ankle bones. Again, very whale-like skull. Skull looks nothing like this. Skull looks more like this. But you still see the leg structures. Here's another organism, an ancient whale that lived about 37 million years ago. Now you see this structure, but we've lost the pelvis and the legs. The rest of the structure is very similar. And then here is a modern cetacean or a modern whale skeleton. The idea of the continents moving, this is called plate tectonics, or the theory of continental drift. Scientists propose that there used to be a supercontinent called Pangaea, where all of the Earth's land masses were together in one big collection. That formed about 237 million years ago by theory, and it stayed that way for about 80 million years, or about 85 million years, and about at the point of about 152 million years ago, the supercontinent of Pangaea began to break apart. The Gondwana is the supercontinent that existed before Pangaea. The Gondwana basically was, there was not a whole lot of life on the planet. Earth's continents were once part of a single supercontinent that split up and drifted apart. This explains how some fossil types can be found on both sides of an ocean. You know, why do we have fossils on this coast, the east coast of South America and the west coast of Africa? Why are their fossils so similar? Theoretically, because at one point those two things were put together. If you actually look at a map or look at a globe, you can see there are areas that should fit together, almost like puzzle pieces. If you look at the sort of hump on the side of South America and then the depression on the west coast of Africa, it looks like you could just take those and fit them together. The outer layer of rock on Earth, the mantle, is arrived in, or it's arranged in layers. It's actually cracked into plates. Yeah, you know, the eastern plate and the western plate and all these different plates. Take a geology course and you'll learn all about those. But slow movement, and we call these things continental rafts. They move to new positions over geologic time, where the plates spread apart. Molten rock comes up from inside. It's basically, these things are separating, and as they do, the molten rock comes up and forms new rock, and it spreads apart. New molten rock comes up and forms. The new molten rock solidifies. Where the plates collide, one slides under the other and is destroyed. So you've got this area where the plates are pulling apart and new rock is forming. And you've got another area where one plate is going under, and as it goes under, it goes into that molten area, and all of this rock will then be melted and eventually work its way back out through one of these separating plates. Areas where we have earthquakes, that is points where multiple plates are butting together. They're sliding back and forth. One plate is sliding under the other, and they kind of hang, and they hang there and build up pressure, and eventually what will happen is that will pop, and what could be at most times a gradual slide suddenly becomes a very violent slide, and that's when you see an earthquake. Plate tectonics, again, here's a picture. Here's where two plates are rubbing together. It's called a fault. Here's an area where there's a weakness in the plate. You see the magma coming up. That's a volcano. You see a trench, a very deep structure that has formed. Here's a ridge, a hot spot, which is where another crack doesn't reach the level of being a volcano, another trench, and another volcano. These are deep ocean V's. Let me hang on just a second. I just got a text from my boss.